is a situation where the magnitude of the population response is going to be smaller, but the speed estimated by the system is faster. And now Mark did exactly what we did before. He took a single speed, he took the responses at those speed, he plotted them a function of the preferred speed of the neurons, and now you can see that here's the bigger population response for smooth motion, and the smaller population response for sampled motion shifted to the right. From this population response, you would estimate a faster speed using vector averaging. That's exactly what the pursuit system does, and so it's proven, right? The pursuit system estimates the preferred speed at the peak of the population response. That's how it figures out how fast the target was moving. Okay, so I'm actually close to finished. This is sort of the conclusion of this in the context of the anatomy. And so here is MT, and what we think is that there is a pathway from MT to the cerebellum, and this visual motor decoding occurs in there, and it is done in a way that looks to us like vector averaging. Now, I want to be really clear about something. I could give you the equation for vector averaging. I don't actually believe that the brain implements that equation explicitly in a way we could recognize. The brain is doing something that we need to figure out that we can model with that equation. That's another layer of the onion. The next step is to peel that layer off, get deeper into it, and figure out how that equation is implemented. Okay, here's another way of looking at it. Sensory representation of visual motion decoding gives us eye direction and speed, MT to cerebellum. Okay, well this is great. This is a reflex, right? There's no thinking in here. But the pursuit system actually is subject to modulation that is under potentially cognitive control, but at least under voluntary control. So we know through experiments that I'm not going to show you, this is a volume control. How many people recognize that as a volume control? This is really what we now know as a volume control, right? That slide was fine in 2000, but nowadays no one knows what the volume knob on an old stereo amplifier does. So here we have the sensory representation, which is decoded. It's then run through a volume control. And so a given sensory stimulus under some conditions will cause a big motor response. And under other conditions, it will cause little or no motor response. And we now understand that as a continuous process that can be graded through modulation of the context in which the stimulus is given. Now, long story short, we know that from experiments done by Masaki Tanaka in my lab that the frontal pursuit area, which is a part of the motor cortex, is responsible for that modulation. So it actually has its fingers on this volume control and is running them around, making it either high or low, depending upon the context in which the animal finds itself. And so we're now down to saying, okay, there's at least two components of pursuit. This has been part of the divide and conquer, right? And we could account for the reflex aspect of pursuit with a visual motor decoding pathway directly from MT to the cerebellum. And that actually left us with extra parts. But now we start to know that those extra parts have other functions. There's another component. There's a volume control. It's up here where more cognitive signals can get access to it. And it turns out that this volume control allows us to choose between two different targets for pursuit. It allows us to use reward to modulate how strongly we respond to a stimulus. And it allows us to... there was one more thing and it slipped my mind. Oh well. Happens. So my conclusions. These are the things I'd like you to take away from this. And if they excite you, I'd like you to think about going into the neurophysiology side of the cognitive science. I think they're all one field. Neural circuits are the basic building blocks of behavior. We can use divide and conquer and simple movements to ask big general questions about how neural circuits work. And that's our goal. I am not interested in eye movements. I am interested in how the brain works. And eye movements are a great tool for me to ask that question. We can take the big challenge of transforming visual stimuli into motor and reduce it to understanding how a population response in a specific area is transformed into activity we can record a few synapses away. In this particular system, we know that pursuit estimates the speed and direction of target motion by computing, I showed you the preferred speed, but also the preferred direction of the neurons that are at the peak of the population response. And I showed you experiments that definitively show that that's the way the system does it. And finally, as part of the divide and conquer strategy, I showed you that two cortical areas that are clearly part of the pursuit circuit mediate two different components of the behavior, one being sort of reflexive visual motor drive and the other modulation. So I need to acknowledge my collaborators. Mark Churchland did the work on apparent motion. Josh Schwartz is responsible for discovering gain control, as is Masaki Tanaka. Yan Yang is recording from the cerebellum. I need to thank Mark, Nick for videos. Don Slaught is a former Major League Baseball player who I had the privilege of coming to know through our common interest in how Barry Bonds hits a home run. And he gave me that illicit video of Barry Bonds, which you won't see anywhere else. It's not on YouTube. David Shopik did the video of me. And my son has been, you know the story. You know the joke, two 15-year-olds standing around, and they're one of them saying, you know, my dad's birthday is next week. I haven't the foggiest idea what to give him for his birthday. What'd you give your dad for his birthday, dude? And the answer is, oh, very simple. I gave him 4 hours of free tech support. Well, my boy provides me a lot of free tech support, and I owe him for finding videos on YouTube and showing me how to get them, extract them, make them into MP4s, and embed them in a PowerPoint video. And research supported by Hughes, National Eye Institute, NINDS, and the Sloan and Source Foundations. Thank you.
Thank you, Steve. God, that was really a terrific talk. I heard his talk yesterday, but I was just as glad to hear it today, and now I think I really understand what he's doing. So we're now going to move to the other end of the cognitive neuroscience spectrum as it concerns vision, and we're going to hear from Brown Hsieh tell us about conscious awareness and how that plays into vision. And I think the comparison between these two approaches is a good one for all of you students to hear. Steve's encouraging you to go into one end of the spectrum, and I'm sure Brown will encourage you to go into the other one. And both ends are just fine and have many, many questions that, as everyone has said, people in your generation are going to answer. So to tell you a little bit about Brown, who is assistant professor in the Department of Neuroscience and Behavioral Disorders at Duke-NUS. He is one of our recently hired young faculty, and we're delighted to have him there, and I think you'll see why when you hear his talk. He did his undergraduate work at National Taiwan University, and then after getting a master's, he moved to Dartmouth College in the U.S., and did his PhD with Peter Hsieh and got his start in the kinds of issues that he's going to be telling you about. He then did postdoctoral work with Nancy Kanwisher at MIT and came from Nancy's lab to Duke-NUS in 2011. So, as you know, his interest is in visual awareness. That's what he's going to talk about. And the title of his talk is, as you see, Causes, Consequences, and Correlates of Neural Awareness. So welcome, Brown. Where are you? Here.
Okay, thanks, Dale, for the introduction. So today I'm going to talk about consciousness. And so yesterday in Professor Brian Shaw's talk, his night talk, there's a great quotation, I believe it's from John Wheeler, saying that in any field, you should look for the most fascinating topic to do your research. And this is exactly the reason I picked the problem of consciousness to be my research topic. So the phenomenon of consciousness has puzzled many great minds across thousands of years in the human history. And even until today, it is still a major unsolved problem in science. And the reason why it is still a major unsolved problem is because it is subjective, okay? Because it has this subjective property or nature in there. And also because of this special subjective property, so the problem of consciousness, it becomes very interesting and puzzling. Because on the one hand, we all know what it is directly from our first person point of view or from our first-hand experiences, because it is this thing that you first experience every day in the morning when you wake up. And it is this thing that disappears when you go to sleep without dreaming. So we all know what it is. But on the other hand, it is also almost impossible to study it objectively because by definition it is subjective. But fortunately, in the past 20 years or so, we have developed so many interesting and novel techniques to study the human brain. So we now have some ability to figure out what it is. And so in this talk, I'm going to give you a very brief introduction about the research on the problem of consciousness and tell you two studies of mine about consciousness. Okay, so let me backtrack a little bit. So what do I mean by consciousness? I'm not going to give you an exact definition of it because I can't do that. So I'm just going to give you a very rough idea about what I refer to when I talk about consciousness. So when people talk about consciousness, usually there are two different aspects. First, they might be referring to this different states of consciousness, like are you fully awake, like right now, or are you totally unconscious, like when you go to sleep or when you are under general anesthesia. So you either have consciousness or no consciousness. And consciousness here means you have experiences or not. Okay? And a different aspect is about that given that you're consciously awake, like right now, so you're fully conscious, but the contents of your consciousness will be different. So for example, we have visual consciousness or auditory consciousness, tactile consciousness, etc. And you notice that I'm using the word consciousness, awareness, or experiences, or qualitative sensations interchangeably. They all mean the same thing. Okay, so, and in this talk, I'm only going to focus on visual consciousness or visual awareness. So, okay, so so visual awareness or visual consciousness refers to those qualitative sensations that we experience visually, like these colorful squares. And I'm going to use this one as a demo to show you that color experiences or color sensations, they are all created in your brain. So they are not actually properties of the object in the world. They are just created by your brain. So all you have to do now is to fixate at the fixation cross and try to fixate really well. And I'm going to turn off the stimuli. So if you fixate well, I believe you will see vivid color sensations even when the stimulus is off. Okay, so this is, you probably all know this is called color after image. And the point of this demo is simply that color sensations, as well as all other perceptual sensations, they are all created by your mind or by your brain, and they're actually not color sensations in the world. They're just created by your brain. So you can all see that, right? Should be a very strong effect. And so now it's really off. So if you saccade around, you can see that it disappears very quickly. Okay, and here's another one called motion after effects. And it's the same thing. So just fixate on the fixation dot there and fixate and wait for a few seconds when the stimulus is off. Then you should be able to see very strong motion after effects moving in the opposite direction. Okay, can you see that? Okay, so this is the same as the color after image, but just in the motion modality. Okay, so the point of that is color sensations, as well as all